Hey everybody, what I'm going to go over tonight is more or less a generalization of what I've been doing about the last 10 days or so. Now, we could have just as well specified the given as the square root of a plus b, where a and b are integers, natural numbers, positive integers. We could just as well have said this is equal to lowercase n, which is some element of the positive real integers, otherwise called are also called the natural numbers, okay? Now, I have a concrete example right here. Notice that 96 plus 25 is 121, and the square root of 121 is 11, all right? And also notice that 96 meets this criterion right here. 96 is equal to 16 times 6. Right? But notice that 16 minus 6 meets this condition. 16 minus 6 is equal to 10, but that's the same thing as 2 times the square root of 25. Okay? So this is one concrete example. One concrete example does not a proof make. So let's see if we can, and again, folks, that's equal to 10, right? And 25 playing the role of b right here. All right. Now, again, the generalization of that is very straightforward. Notice that if we start with this, the square root of a plus b is equal to n, and square both sides, we get this statement right here. And it all just washes out very nicely at this stage, since this is a very well-known difference of two squares. So we can write this as n plus the square root of b. Okay, that's quantity, and then n minus the square root of b. Again, I've done quite a few numerical examples of this, but this is the first time. It's not particularly hard, but it's kind of fun to me, kind of interesting. All right, now notice, so we've written a is the product of these two factors, but it's very clear that n plus the square root of b, which is the first factor there, minus n minus the square root of b, the n's cancel, and we end up with what we were looking for. This would be 2 root b. And if we go back to the top here, you'll see that's what we were, it's a b there, okay. 2 root b, and that is what we were trying to do right here. Yeah, the very same thing holds if we replace n with the rational numbers, that you get nested radicals on those type of problems. But nothing about this algebra would fail if we were working over the field of rational numbers. Okay, so again, this is just, we're sticking to integer or positive integers, but we could also, the very same kind of result would apply to the rational numbers. Okay, thanks for viewing.